Good morning, everyone. I'm a master's student at Visual Computing Research Center, Shenzhen University. Today, I'm glad to present our work introducing unbiased depth into 2D Gaussian splatting for high-accuracy surface reconstruction. This work focuses on significantly improving the geometric reconstruction quality of 2D Gaussian splatting. First, introducing our research. The focus of our work is multi-view 3D reconstruction, a classic and fundamental task in the field of computer vision. This task typically starts from multi-view images with known camera poses and employs various algorithms to reconstruct high-fidelity 3D models of target objects or scenes. Among traditional approaches, structure from motion is one of the most representative methods. However, such conventional techniques often fail in textureless regions, resulting in reconstructed surfaces with large holes or incomplete geometry. In recent years, the emergence of neural radiance fields and 3D Gaussian splatting has revolutionized the field. A number of novel reconstruction methods based on these techniques have been proposed, significantly improving the quality and completeness of 3D reconstruction. Methods based on neural implicit fields typically achieve very high accuracy. For example, Neuralangelo leverages hash encoding to precisely recover fine object details. However, a common challenge across such methods is their prohibitively long optimization time, often requiring dozens of hours to reconstruct a single 3D object. This largely hinders the practical deployment of these techniques. On the other hand, methods based on Gaussian splatting have gained increasing popularity in both academic and industrial communities. Their primary advantage is faster reconstruction speed compared to NeRF. To extract reliable surfaces during reconstruction, most Gaussian-based techniques intentionally flatten the 3D Gaussians and align them closely with the object surface, such as Sugar, 2DGS, and PGSR. First, let's discuss Sugar. This approach utilizes a regularization term to flatten the 3D Gaussians, aligning them closely with the object surface. It then samples surface points by applying a uniform threshold. However, due to the inherent volumetric nature of Gaussians, this sampling process often introduces noise, resulting in suboptimal reconstruction quality with artifacts and inconsistencies. NeurSG jointly optimizes both Gaussian representations and neural implicit surfaces. But the key challenge remains how to effectively synchronize the training speeds of these two distinct methods. Gaussian opacity field reconstruct an opacity field derived from 3D Gaussians, so naturally this method still suffers from the inherent limitations of volumetric Gaussian representations. In PGSR, the incorporation of multi-view geometric and photometric consistency has led to a substantial improvement in the reconstruction quality. Nowadays, Gaussian-based methods have been steadily surpassing NeRF-based approaches, reflecting a clear trend of technical advancement. One notable work presented at SIGGRAPH 2024 introduced a variant of 3D Gaussian splatting, which also serves as the foundation of our research. Unlike 3DGS, this method utilizes 2D Gaussian planar disks as primitives rather than 3D Gaussian volumes. During the rasterization stage, it directly computes the precise intersection points between the camera rays and these disks, completely eliminating the perspective distortion caused by A-frame approximation in 3DGS. By incorporating additional depth and normal regularization terms, this method achieves considerably higher geometric reconstruction quality compared to 3DGS, making it particularly suitable for high-fidelity surface reconstruction tasks. Now introducing our method. Let's begin with the limitations of 2DGS. During surface reconstruction, we frequently observe large holes and pits on the reconstructed surfaces, which triggered us to investigate further. Upon closer inspection, we found that these defective regions are predominantly located at highlight spots on glossy or semi-glossy surfaces, such as the specular reflections on fruits, or smooth planar surfaces. In multi-view settings, these areas exhibit extreme brightness only when observed from a very limited range of viewpoints. This introduces high-intensity variations that violate the multi-view consistency assumption, which is detrimental to accurate geometry reconstruction in Gaussian splatting. As a result, the presence of such specular highlights significantly misleads the training process, leading to severe geometric inaccuracies and artifacts in these critical regions. If we examine the distribution of Gaussian primitives in these regions, take this scene as an example, we can observe that a small number of low-opacity Gaussians are distributed near the true surface, while a large number of high-opacity Gaussians are concentrated inside the object. Clearly, these internal Gaussians are primarily responsible for reconstructing high specular reflections. This schematic demonstrates why strong specular highlights lead to such a spatial distribution pattern. Although spherical harmonics are used to model view-dependent color, low-order spherical harmonic functions struggle to represent high-frequency specular reflections. To compensate for this, the optimization process relocates high-radiance Gaussians inside the object so that they are only visible within a narrow range of viewpoints, effectively mimicking the behavior of high-frequency specular highlights. Therefore, to reconstruct the geometry of these regions more accurately, we aim to adjust the spatial distribution of Gaussians, encouraging more primitives to concentrate near the true surface. One of the methods we propose is the convergence loss. In the rendering pipeline of 2D Gaussians, the raised planar intersections are computed explicitly. The loss function encourages adjacent intersection points to converge toward each other. We use the minimum of Gaussian function values at these 2 points as ways to guide its optimization process. It is worth noting that 2D.js also introduced a loss function to consolidate Gaussians. Their regularization term similarly encourages the convergence of intersection points along each camera ray. However, unlike our approach, they weight this process using the opacity of the Gaussians. In contrast, we intentionally exclude opacity weighting in our formulation. This design is motivated by our earlier analysis of highlight regions. Low opacity Gaussians tend to distribute near the true surface, while many high opacity Gaussians are pulled inside the surface due to specular reflections. By avoiding opacity-based weighting, we prevent these inwardly recessed Gaussians from dominating the optimization. Instead, our method treats all Gaussian primitives equally. This figure illustrates the Gaussian distribution within a glossy region after the application of the convergence loss. It can be observed that our method successfully increases the density of Gaussian primitives near the true surface and effectively attracts nearby Gaussians to converge onto the surface. This convergence behavior directly facilitates more continuous and complete reconstructions. After applying the convergence loss, we observed a significant increase in the density of Gaussians on the surface in highlight regions. However, their opacity still remains relatively low. When using conventional methods to render depth maps, this layer of low opacity Gaussians may be omitted. Since TSDF-based mesh extraction heavily relies on accurate depth maps, this limitation adversely affects the overall reconstruction quality. To address this issue and further improve the results, we propose a novel depth estimation method as our second key contribution. Simply put, as a ray passes through the primitives, we compute a modified cumulative opacity by adding a small constant offset to each Gaussian's opacity. This offset is introduced to account for the number of intersected primitives along the ray, ensuring that even low opacity Gaussians contribute meaningfully to depth estimation. A predefined threshold determines the stopping point, and the corresponding depth at the intersection point is taken as the depth value. From the comparative experiments, we can observe that adding a constant offset significantly reduces holes in specular regions. So what is the underlying principle behind this improvement? In specular areas, under non-overexposed viewing angles, subtle textures of the surface, such as scratches or dust on metallic objects, remain visible. These features allow Gaussians to distribute correctly near the true surface. However, in certain viewpoints, excessively strong highlights suppress the opacity of these Gaussians, causing depth estimation methods that rely solely on opacity to fail. Our approach is by explicitly accounting for the density of Gaussians along the ray, successfully captures these surfaces even under high-intensity specularity. This is achieved through the constant offset, which ensures that low opacity yet geometrically meaningful Gaussians contribute to the depth estimation. Now, introducing our results. We conducted evaluations across multiple datasets and compared our methods with 2D GS. As shown here, we present the reconstruction results on the object-centric DTU dataset. First, we present non-metallic surfaces with specular highlights. While 2D GS struggles to faithfully reconstruct the highlight regions, our approach successfully captures these challenging areas with notably improved accuracy. Next, we present objects with metallic surfaces. Although some materials exhibit highly polished surfaces, as long as they are not perfect mirrors, it remains possible to reconstruct their geometry by leveraging multi-view consistency. This is clearly demonstrated in the successful reconstructions of Object 37 and Object 97, where subtle surface variations provide sufficient clues for reasonable mesh extraction. While our algorithm is specifically designed to handle specular highlight regions, it does not compromise the reconstruction of surfaces with high roughness materials. In fact, for such materials, we achieve reconstruction quality comparable to, and in many cases even superior to, the results obtained by 2D GS. This demonstrates the robustness and general applicability of our approach across varying material properties. Evaluated on the DTU dataset, our approach demonstrates superior performance over other Gaussian-based methods in key metrics, with only a modest increase in computational cost. We have also evaluated our method on scene-level datasets, where local overexposed highlights frequently occur. Our approach effectively suppresses the interference from these artifacts, ensuring more stable and reliable reconstruction results under challenging lighting conditions. We have also evaluated the performance of our method on novel view synthesis. On the MIPNERV 360 dataset, our approach achieves a comparable overall metrics to 2D GS. Additionally, we observe that our method demonstrates better accuracy in reconstructing planar regions. For local dense and cluttered areas, such as complex vegetation, methods based on 2D planar Gaussians struggle to achieve high-quality reconstruction. Our proposed regularization does not adapt well to these intricate geometric structures. Our evaluation demonstrates that the proposed method achieves comparable performance to 2D GS in novel view synthesis accuracy. 2D GS uses a position where the transmittance decays to 0.5 as a depth value for a pixel. We attempted to increase this threshold to allow low opacity Gaussians to contribute more effectively to depth estimation, but this did not improve reconstruction quality. However, when we replaced the depth determination method with our approach, a significant improvement in reconstruction accuracy was observed. In this work, we conducted a detailed analysis of the challenges faced by 2D GS when reconstructing glossy surfaces with specular highlights. To address these issues, we introduced two key solutions: a novel loss function that consolidates Gaussian primitives toward the true surface, and a new depth estimation strategy that robustly identifies surface locations even under strong specularity. Our approach markedly enhances geometry reconstruction accuracy, effectively overcoming the limitations of 2D GS with only minimal additional computational overhead, ensuring comparable training efficiency. The limitations of our approach lie in its inability to handle mirror reflections and excessively cluttered geometries. Our code has been publicly released and is available for reference and use by the community. Thank you.